everybody, this is Group 44's presentation on the industrial production of DDT. I'm Jed, and I'd like to give a thank you to Prince and Rosaline for their invaluable output in this presentation. Without them, I could not do this. And a shout out to Dr. Jude, the finest chemical engineer in this university and possibly the whole universe. Thank you very much. Happy belated birthday. So let's get started. So, DDT, or dichloro-diphenyl trichloroethane, is an organochlorine compound consisting of two benzene rings substituted with two chlorine atoms and linked with three chlorine atoms, a very big molecule. It was first synthesized in 1874 by Othmar Zeidler, the man on your right, but found its powerful insecticide properties only in 1939 through the work of Swiss chemist Paul Hermann Müller, the other man on the left. DDT became widely used as a pesticide, particularly during World War II, where it was instrumental in controlling malaria and typhus. Unfortunately, DDT is banned because of its harmful environmental and health effects. But in some cases, it is allowed and it is used. So, by investigating the industrial scale production pathway, we develop a better understanding of large-scale organic synthesis and reaction engineering and environmental management associated with chlorinated organics. So let's get started on the nitty-gritty, how to produce our DDT. So quickly, to create DDT, all you have to do is four simple steps. You take benzene, you add chlorine to it. You take ethanol, you add chlorine to it. You take those two things and you smash them together and you get your DDT. The rest can be explained in the PFD. So this will get to the nitty-gritty of how we take that and form an actual product. So the starting material feed is one of the first steps. Then we separate it in the separation step. Then the condensation, cooling and crystallization, filtration, drying, product storage, and waste treatment. So on those steps to create our DDT, and we'll explain that later on in this video. So first step, the feed section. This is first creating our chlorobenzene for our DDT. So we take benzene, we pass it through flow control valve, that's a tap to control the flow rate. Pass it through a filtration column to get rid of any impurities, and at the intersection below the compressor, chlorine gas is passed over it and into the AlCl3 fixed bed reactor to create our chlorobenzene. Very simple. The same thing is done for ethanol to form chlorol. So ethanol passed through flow control valve, through filtration, underneath compressor, through the fixed bed reactor to form chlorol. So that's ethanol and chlorine. Makes sense. The next step is that from chlorobenzene and the chlorol, we purify it. So from the AlCl3 bed, pump into a gas liquid separator that heats it up and separates your byproducts, in this case HCl, to your water starch tank, so it dissolves, goes away, and we can get a beautiful chloral stream in our distillation column and up and away back into the process. All waste is directed back towards a waste treatment center. Then cooling and crystallization. So when you have chlorobenzene done, chloral done, you have sulfuric acid for the reaction. You pass it through a mixer. It acts like a big blender, just mixes those two together and into a condensation reactor where the magic happens. That is where your DDT is formed. But even when DDT is formed, it still comes with a lot of impurities. So cooling and crystallization basically removes those impurities. You go through the crystallizer. Crystallizer passes through chilled water circulation to the cooling tower, so that keeps your DDT in a solid form and all the rest of the gunk outside and as a liquid. You pour all of that liquid off in the decanter. The decanter pours the liquid off to the water storage tank and the DDT into the washing unit. Think of it as like a big dishwasher. It will heat, clean, and evaporate all the other nonsense off the DDT. The DDT from that wash state, it goes into the drying unit. So it's not really a crystal, it's more of a powder. So that's more getting rid of the intrinsic water. From then down into the DDT storage tank. So very simple process, very effective. Very cool. Down. So when you put everything together, you get this beautiful, elegant, yet simple diagram. From the feed section on the left to the mix section in the middle, and then your processing section on the right. Your waste treatment center, as you can see, is in your bottom right, where all of the waste goes to be filtered and do all its random other stuff. Very simple. Now, we get to the meat and potatoes of PFD design, instrumentation and control system design. So at every single level, so at every stream, at every vessel, at every pump, there has to be a specific operating conditions. These conditions, temperature, pressure, pH, and other stuff must be controlled. So we will get to know how this is controlled in our DDT chemical plant. So here, key parameters: temperature, we mentioned; pressure, flow rates, very important; pH sensors, and level indicators. At every single level, certain reactions only occur and are optimal at certain reactions, at certain temperatures. So, for example, recondensation, 30 to 50 degrees Celsius, certain pressures, maybe 15, 25 bars of pressure. You need to be very careful. Flow rate is for optimization, so you don't go way too much where you destroy your plant, and also you don't go too little where you're not producing enough product. pH sensors, so when it comes to catalysts, certain catalysts work in certain pHs, we know that. And level indicators, so that managers, administration, and operational workers can tell what is happening and how much of everything is actually flowing. So just basic administrative stuff. So after this, we get the control systems, which is basically that's how we automate this plant without having to literally be there all the time. So we have automated valves used to regulate reactant feed based on flow and temperature feedback, controlled via local logic controllers, or PLCs. PLCs are programmable logic controllers, basically just how you run it using a sort of AI, a computer. Makes sense. Agitators and mixers, so that's just your mixers, but this time automated, so automated blenders if we have those. And heat exchangers and cooling jackets, exceptionally important in DDT. So DDT, again, you have to crystallize it afterwards, and the runaway heat can be a problem. You can either melt the reactor sometimes, or it can cause other reactions to just either go way too haywire, which can cause other problems with pressure, which we'll see later on in the video. Okay, good. Safety systems, as we can see, pressure, if it's too much, sometimes it can cause explosions. So emergency shut valves are installed inside the plant to make sure that if any pressure is too much, the pressure can be released. Relief valves and rupture discs do the same thing. Gas detectors and HCl scrubbers are to remove any runway gas, any runway HCl, so it doesn't kill your workers and destroy the environment again. Makes sense. So at every single level, even when we have the PFD, we must control these operating conditions very, very carefully. And we can do that through control, system, and instrumentation design. Okay, good. Now, let's get into the part that Dr. Jude loves the most: networking and computer infrastructure. So, basically, we have a plant. We are in the 21st century, so there's a way we can control this using IT technologies and remote sensors. This is where our networking and computer infrastructure comes in. A bit technical, but stay with me, it's going to be very simple. So, systems control and surveillance. CCS architecture is direct distributed control systems. These are ways of centralizing control of the whole entire plant, so you can control these things without being directly there and yet still have general administrative power over the entire plant. The SCADA integration. Now, SCADA is very different. Let me get up here and get the name. SCADA stands for Supervisory Control and Data Acquisition. So basically, a big spreadsheet of what's going on these things. PLCs, programmable logic controllers, connect to a central SCADA system via secure protocols. So basically, if you need to know what's going on, the SCADA, basically a big spreadsheet, just imagine like that, controls these things and allows you to tell what's going where. Control rooms, which HMIs, display real-time data, trends, and alarms. Operator functions, same thing, alarms, emergencies, you get it. Networking, for real-time monitoring, surveillance of the plant, and an in-house network system is integrated to maintain optimal operational conditions, maintain safety, and facilitate and plant operation. Good. So with all of these things being said, thank you very much for the time you've taken to listen to this with DDT production and DDT industrial production. Appreciate very much for listening to this, and thank you.